What if the sun vanished for just 1 second? Not dimmed, not eclipsed, gone. Every photon, every particle, every ounce of its mass, erased for 1 single second, then instantly restored, exactly as it was. No damage, no aftermath, just a 1-second blink in the life of a star that has burned for 4.5 billion years. Would you see it happen? Would the sky go dark? Would Earth lurch out of orbit? Let's find out what would actually happen. Let's set the rules first. The sun disappears completely for exactly 1 second. Every form of energy it produces, light, heat, gravity, all of it, switches off at the same instant. After that 1 second, it reappears exactly as it was, with no missing time, no shift in its internal processes, nothing. This isn't a slow fade, it's an instantaneous flicker. On, off, on again. And the question we're really asking is simple. In that 1 second, does the rest of the universe even notice? Start with the obvious guess. Surely you'd see it. Surely the sky would go black, even for a heartbeat. But here's the first problem with that assumption. The light hitting your eyes right now already left the sun 8 minutes and 20 seconds ago. You are never looking at the sun as it is. You are looking at the sun as it was, 8 minutes in the past. So if the sun vanished at this exact moment, what would you see? Nothing different. Not yet. The light already in transit, already streaming across 93 million miles of space, keeps arriving on schedule. It doesn't know the source is gone. It just keeps traveling. This is where the astrophysicist John Bacall's decades of solar research become useful. Bacall spent much of his career mapping exactly how energy moves inside the sun, and one of the strangest findings from that field is this. The light you see leaving the sun's surface today didn't start there. It began as a burst of energy deep in the solar core, and it took somewhere between tens of thousands and a few 100,000 years just to fight its way out to the surface, bouncing between particles in a chaotic random walk before finally escaping into space. Only then does it begin its 8-minute sprint to Earth. In other words, the light warming your skin right now is a fossil. It's ancient, and that means a 1-second gap in the sun's output, however total, would simply vanish into a pipeline that's already hundreds of thousands of years long. You would never see the gap. It would be smoothed away before it even had a chance to reach the surface. So light is a dead end. What about gravity? Surely that's different. Surely if the sun's mass disappeared, even for a second, Earth would feel it immediately. Some invisible tether suddenly slack, sending our planet drifting off in a straight line into the dark. This feels like it should be instant. Gravity isn't light. It's not a beam you can see or block. It's the shape of space itself, bent by mass. Wouldn't that bend simply snap back the moment the mass was gone? Here's the twist almost nobody expects. Gravity doesn't travel instantly either. According to general relativity, changes in a gravitational field propagate at exactly the same speed as light. Not faster, not instantly, the same speed. This isn't just theory. In 2002, the physicist Sergei Kopeikin used a chance alignment of Jupiter passing in front of a distant quasar to actually measure how fast gravity's influence moves through space, and the result matched Einstein's prediction almost exactly. Gravity crawls across the universe at the speed of light, just like every photon leaving the sun. So if the sun's mass vanished for 1 second, Earth wouldn't feel a wobble right away. That change in gravity would have to travel the same 93 million miles that light does, arriving 8 minutes and 20 seconds later, just like the light. And by the time it arrived, the sun would already be back. The 1-second gap in gravity would ripple outward as an infinitesimally brief, essentially undetectable pulse, smaller than the everyday gravitational nudges from Jupiter, the moon, or a passing truck outside your window. Earth's orbit wouldn't lurch. It wouldn't even blink. So the sky stays lit. The orbit stays steady. Is there truly nothing left to notice? Actually, there's one messenger we haven't accounted for. One that doesn't play by the same rules as light. Deep in the sun's core, nuclear fusion doesn't just make light, it makes neutrinos. Ghostly subatomic particles produce the instant hydrogen fuses into helium. And unlike photons, neutrinos barely interact with anything. They don't bounce around inside the sun for hundreds of thousands of years. They pass through the sun's entire mass in about 2 seconds, as if it weren't even there, and then race outward at very close to the speed of light. That means the neutrinos reaching Earth right now aren't a fossil from ancient history. They're a live broadcast, roughly 8 minutes old, not 800,000 years old. This is where things get interesting. If fusion in the sun's core actually stopped for 1 second, that gap would show up in the neutrino stream, leaving the sun almost immediately. It would then travel outward and arrive at Earth about 8 minutes and 20 seconds later, riding alongside the light and gravity we already tracked. For one brief second, the number of solar neutrinos reaching Earth would dip, ever so slightly, before returning to normal. Could anyone actually catch that? This is where the work of Raymond Davis Jr. and Masatoshi Koshiba matters. Davis spent years running a solar neutrino detector deep inside a South Dakota mine, and Koshiba built the Kamiokande detector in Japan, both hunting for these nearly invisible particles streaming from the sun's core. Their work eventually earned them the Nobel Prize in Physics, and it proved that solar neutrinos really can be caught here on Earth, in extremely small numbers, using massive underground tanks of ultra-pure water or liquid, designed to catch the rare occasions when a neutrino actually interacts with an atom. Modern successors to their detectors, like Super Kamiokande, register solar neutrino interactions constantly, but only a tiny handful per day, because neutrinos so rarely interact with anything at all. A 1-second dip in the flood of neutrinos leaving the sun would translate into, at most, 1 or 2 missing detections, buried inside a sea of ordinary statistical noise. In theory, it's the only physical evidence anywhere in the universe that the sun blinked. In practice, unless a very lucky detector happened to be listening at exactly the right instant, that evidence would slip by completely unnoticed, indistinguishable from an ordinary quiet moment in the data. Now push the scenario further. What if you weren't standing on Earth at all? What if you were an astronaut hovering just above the surface of Mercury, less than half the distance to the sun that Earth sits at? Light and gravity would still be crawling at the same fixed speed, but the trip would be shorter, only about 3 minutes and 20 seconds instead of 8. You'd notice the gap sooner, but you still wouldn't notice it instantly. Even standing on the closest planet in the solar system, you'd still be watching a 3-minute-old rerun of a star that already came back before the bad news finished arriving. Now flip it the other direction. Imagine a probe drifting near Neptune, 30 times farther from the sun than Earth is. Out there, the light delay stretches past 4 hours. A 1-second gap in the sun's output would arrive as such a vanishingly small ripple in an already faint, already delayed signal that it would be utterly lost, a rounding error swallowed by distance itself. The farther you get from the sun, the more its now becomes pure fiction. There is no version of the solar system where anyone, anywhere, catches the sun in the act. Even the ground beneath your feet wouldn't help. You might assume the oceans would answer for you. Tides are a gravitational conversation between Earth, the Moon, and the Sun, so surely a missing sun for 1 second would show up as a strange hiccup in the tides. But tides build up over hours through the slow, cumulative pull of gravity acting on enormous bodies of water. A single missing second, arriving 8 minutes late and lasting only a heartbeat, wouldn't so much as ripple a puddle, let alone an ocean. The sea has no memory for something that brief, and neither does anything else built on a timescale longer than a second. That leaves the neutrinos as the closest thing to a live witness, and it's worth understanding just how faint that witness really is. Detectors like Super Kamiokande in Japan and the newer Ice Cube Neutrino Observatory, buried deep in the Antarctic ice, are built specifically to catch these ghost particles as they pass through, using enormous volumes of water or ice to maximize the odds of a single interaction. Even so, on an ordinary day, the sun sends an almost incomprehensible number of neutrinos through Earth and through your own body, and detectors still only manage to register a tiny fraction of them because neutrinos pass through solid matter as if it were empty space. A 1-second gap in that flood would be real, physically real, racing outward at nearly the speed of light, exactly like everything else. But asking a neutrino detector to notice one missing second inside a constant, thin drizzle of nearly undetectable particles is like asking someone to notice one raindrop missing from a passing storm. The evidence would exist, it just wouldn't be legible to anyone. So gather everything together and ask the real question. If the sun vanished for 1 second, would anyone, anywhere, actually know it happened? The light wouldn't fade, because you're always watching light that's already ancient by the time it leaves the sun's surface, and the 1-second gap gets swallowed inside a journey hundreds of thousands of years long. The gravity wouldn't shift, because gravity crawls across space at the same speed as light, arriving 8 minutes late and rippling through as a change too small to ever separate from the sun's constant, ordinary gravitational hum. And the only true real-time signal, the neutrinos, would carry the truth outward at nearly the speed of light, arrive 8 minutes and 20 seconds later, and then almost certainly vanish into statistical noise, caught by nobody, noticed by no one. Think about what that actually means. Every single thing you know about the sun right now, its light, its warmth, its pull on the planet beneath your feet, is old news. You are living inside a very slight delay, watching a rerun of a star that finished doing what you're seeing 8 minutes ago. Your entire experience of the sun is, quite literally, a message from the past, and it always has been. You already live with delays like this every single day, even if you never think about them. Look up at the night sky, and some of those stars burned out thousands of years ago, their light only now completing its journey to your eyes. A voice call routed through a satellite carries a barely perceptible lag as it climbs to orbit and back down again. Even the GPS signal guiding your phone right now is a message from a satellite in the past, corrected constantly for the split-second delay of its own journey to you. The sun is just the closest, brightest example of a rule that governs the entire universe. Nothing you observe is truly happening right now. It's always a report, arriving fashionably late. So what if the sun vanished for just 1 second? The truest answer isn't dramatic. It isn't a flicker in the sky or a jolt through your body. It's this. You would never know. Not because nothing happened, but because by the time the universe finished delivering the news to you, the sun would already be exactly as it always was, quietly burning, 93 million miles away, 8 minutes and 20 seconds ahead of everything you'll ever see.